as again WL by, let's say, AE. So the deflection due to dynamic loading is definitely dependent on this velocity factor, right? In case of static loading, the deflection was not dependent on the velocity factor, as there was no velocity at all at the point of impact. So deflection here will be definitely governed by kinetic energy. Now let us try to find out the stress that this bar is subjected to. Now the stress is basically given by sigma by E is equal to delta by L, right? So delta dy, I should say, by L. So sigma is equal to delta E by L, that is E by L, that is into delta dy, that is this thing, into, I should say, if I bring this also in the root, I should write it as E squared by L squared, WL by AE into V squared by G. Now L cancels out, E squared E cancels out. So I will write sigma here to be equal to WV squared by, I should say, it will be equal to WV squared by G into WV squared by G into E by AL, or I should write it as 2E by AL and 2G. So this gives me, this is a factor, WV squared by 2G is basically my kinetic energy. So stress, tensile stress or compressive stress in this bar is essentially a function of the kinetic energy and also the function of modulus of elasticity and length. So in case of static loading, what we saw essentially was that the stress is a function of essentially the load and the cross-sectional area. But in case of dynamic loading, we just saw that it's a function of definitely the kinetic energy, the elastic modulus and length, and also the cross-sectional area. So this is where dynamic loading is different than static loading, in the effect that in case of static loading, equilibrium is maintained at every stage. There is a slow incremental increase of load, right? But in dynamic loading, it's like this. The weight falls bang on the bottom flange with some velocity and it is deflected, right? And I have the stress in the bar to be directly proportional to the kinetic energy of this falling weight, right? Now let us now see a case wherein we get the two, static and dynamic loading. Let us see that. Example, if I have again some kind of an arrangement like this, and suppose this is my prismatic bar, and I put a weight of W on, say, this bottom flange, right? Now what will basically happen is that first it will be a case of static loading, because once I put the suddenly applied load, obviously the body will be subjected to some kind of a deflection. So due to static loading, let's say that this is equal to delta St, and if the weight W is applied, therefore delta St is equal to nothing but WL by AE, and it deforms, I should say, till this position, right? Now at this point, what basically happens is that the potential energy that this body had is converted to kinetic energy. So at this point, this body will acquire some velocity, and as we know, if the body acquires some velocity at the point, so essentially this velocity or this kinetic energy will be strong enough to drive the body through a deflection, right? So essentially will drive the body to some sort of a deflection, and let's say that this deflection is delta dash. Now whether we can find out delta dash or not, we will see. Now we know that delta dy, so this is a case of dynamic loading, and we know that delta dy is essentially equal to delta St plus delta St whole squared plus 2h into delta St, or I should write it as in the form of V squared by G. So at this point, essentially the velocity at this point will be 0, because this point corresponds to the position of equilibrium. So at this point velocity will be essentially 0, and I can rub this factor out. So if I sum it up, it will be equal to 2 delta St. So if we apply a certain kind of a suddenly applied load, right, then what will happen is that the deflection will be 2 times that of static loading, right? So this is essentially some sort of an amalgamation of dynamic and static loading in this case. And essentially, so the brief synopsis is like this, that in case of static loading, every increment of load, there is a corresponding increment in deflection. and there is no suddenly applied load as such, right? So what happens basically is that at every stage equilibrium is necessarily maintained, right? But in case of dynamic loading, what happens is that there is a velocity factor creeping in, or the kinetic energy factor creeping in, which drives in some deflection, right? So essentially, till this point wherein the velocity is not equal to 0, we don't have equilibrium, but we definitely have equilibrium at the point wherein this velocity will be equal to 0, as we can easily picturize, right? So this is all for this lecture. Thanks a lot for listening. Thank you.